Welcome back, and today we're going to be starting to look at our journey into volumetric analysis and standard solutions. First up, of course, is looking at standard solutions and how the equipment that we use for volumetric analysis. With volumetric analysis, we're relying on chemical reactions between substances that occur in solution. So this is a bit different to gravimetric analysis where we mix two solutions together to get a precipitate. Now the reaction is going to occur in solution and stay in solution. So we're not going to have necessarily something physical that we can weigh or otherwise. We need another way to be able to detect what's going on in the reaction. For this, generally, the amount of mole of an unknown substance, so this would be like our water sample, is analysed by reaction with a solution of a known substance of known concentration. And this is really important that it is an accurately known concentration that we're doing our titration or our volumetric analysis with. It's generally considered a faster and more convenient technique than gravimetric analysis because we don't have the drying steps. We don't have to dry it multiple times in order to be able to get the result. And it's just these reactions tend to go a bit faster and it's a bit easier to set up. We do use a large amount of glassware for volumetric analysis, some of which you've seen before, which are our beakers and conical flasks. The conical flask in a titration often referred to as the titration flask or the analysis flask. There can be measuring cylinders is used, and then we have these new pieces of equipment here, which are all what we call volumetric glassware, and we will look at these in more detail as we go along. But this is a volumetric flask, and these have a fixed volume. So you will notice with these that they don't have gradations up the side like our measuring cylinders do or anything like that. They just have one calibration mark, and this is because it will only accurately measure out one volume, often 250 mils or 200 mils, which are the ones that we commonly have in our laboratory at school. And the same for the pipette here. So this is a glass version of those disposable squidgy pipettes that we've used previously, but these are far more accurate and deliver only one volume. And then this one here is a burette, and we will learn more about that later on. You can see it has a gradation, so it delivers a variable volume. Okay, so there are a number of things that we need to consider in terms of vocabulary for this, and it is important that we know what we're referring to in using this vocabulary. First is standard solutions. So standard solutions are solutions containing an accurately known amount of an analyte or the concentration. So this is one where it is made up in the lab accurately, okay, so that we know the concentration. The standard solution is always of a known concentration. This is going to be the reference for us to determine the unknown. Okay, so if you think back to stoichiometry, if we're doing solutions, we're probably going to be doing acid and base chemistry. So if we have an acid plus a base, we get salt plus water. If I accurately know the concentration of one of these, okay, and then I know what volume of it reacts, I can then work out the concentration of the other one using stoichiometry as we did with gravimetric analysis. So the accuracy of the measurement, okay, refers to how close it is to the true value. Okay, so usually this means we'll have comparisons to literature values or perhaps recommended daily intakes or governmental guidelines or things like that. Okay, so how accurate our analysis is how close we are to the true value. Determining the accuracy of this measurement requires calibration of the analytical method, i.e. having a standard. Okay, and we've done this when we talked about standards with AAS and UV-Vis to make our calibration curves or standard curves. So again, this is using standards to help us determine the concentration of an unknown in solution. So primary standards by definitions are reagents that are so pure the amount of substance can be accurately calculated from its mass. Okay, so we buy them in high purity, and they have a number of criteria that they must meet to be considered a primary standard. this is they need to be readily available in pure form, so we need to be able to buy or make them in very high purity. They need to be easy to store without deteriorating or reacting with the atmosphere. So they need to be stable for a long period of time. Okay, so they're not going to react. They need to have a known formula. So we want them to be able to be dry, not something like copper sulfate, pentahydrate, which depending on how it's been stored may be drier than that or not. Okay, so we generally avoid hydrated compounds. They must be anhydrous in order to be a primary standard, so no water. Generally, they're stored in a desiccator to ensure that they stay dry. And usually, because we're going to be using them quite a lot, they need to be inexpensive with a high molar mass so that we're not weighing out very small masses when we're trying to make a reasonable concentration. Okay, generally we want to be weighing about 1 gram or 2 grams because that's a nice easy amount for us to be able to weigh out with our clumsy fingers. We don't want to be weighing out like 0.01 grams in order to get a 1 molar solution or something like that. Okay, so it's got to have a high enough molar mass that we can weigh it out easily. So there are primary standards, and there are a number of things that can't be used as primary standards because they will react. The example I used before in an analysis that we might do between sodium hydroxide and HCl, in this case, neither of these compounds would actually be suitable to be a primary standard. Sodium hydroxide is a strong base and will react with carbon dioxide in the atmosphere. So if we store, or even while we're actually weighing out sodium hydroxide, it will be reacting with CO2 in the atmosphere to form sodium hydrogen carbonate, no longer sodium hydroxide. Okay, this can also form things like sodium carbonate over time. The other thing is that sodium hydroxide is what we call hygroscopic or deliquescent, which means it absorbs moisture from the air. So the longer we have it, if it's a humid environment, the longer we have it sitting on the bench, the more moisture it's going to absorb, so the more inaccurate the mass as we try and weigh it out. Okay, so sodium hydroxide, definitely not something we can use as a primary standard because its concentration will be changing quite quickly in terms of over the course of our experiment. The same goes for strong acids. They are only purchased in a concentrated form, not a pure form. Okay, so you'll notice when we use sulfuric acid, concentrated sulfuric acid in our acids and bases unit, it was concentrated sulfuric acid, which is about between 6 and 10 molar, and then HCl, again, we use 10 molar, but these weren't pure, so we can't get hold of these strong acids in pure form. So again, they're not suitable to be used as primary standards. This means that before we use them in an analysis, we would have to standardize them, i.e. find their true concentration by reacting them with another primary standard. In order to prepare a primary standard in the laboratory, we need to be able to put in an accurate mass. Okay, so we prepare the mass of the substance. We place it into a volumetric flask. As I said before, these accurately measure out to a specific volume, not a variable volume. We will fill the volumetric flask about halfway and then shake to dissolve as much of that solid as we can. Once that's all dissolved, we will then fill up to the calibration line. Okay, there will be a calibration line on the actual ground into the glass. And of course, the meniscus needs to sit on the calibration line. If we go over, then we'll need to start again because the concentration won't accurately be known. We will have put more water in there than what our flask was calibrated for. So we make the solution by dissolving an accurately known amount into a known volume using an accurate volumetric or standard flask. On the next part of this video, it's actually going to play a setup of a standard solution done by the Royal Society of Chemistry. This will show you experimentally how this is conducted.
Before you carry out your titration, you'll need to make up a standard solution. That's a solution of a known concentration. In this case, we'll be making up a solution that's about 0.1 moles per decimeter cubed sodium carbonate in a 250 centimeter cubed volumetric flask. In this video, we'll run through the steps required to make up your standard solution, including all of the measurements and calculations you'll need to carry out to get the exact concentration of your sodium carbonate solution. To make up the standard solution, it's necessary to know accurately the exact mass of sodium carbonate, which will be dissolved in a known volume of water. The best way to do this is via a method called weighing by difference. Using a spatula, measure out approximately 2.6 grams of anhydrous sodium carbonate. Record the mass of the sodium carbonate with the weighing boat. Transfer this solid to a 100 centimeter cubed beaker. Reweigh and record the mass of the used boat. Using these measurements, you can calculate the exact mass of anhydrous sodium carbonate. Next, take this anhydrous sodium carbonate and dissolve in distilled water from a wash bottle. Stir this solution thoroughly until the solid is completely dissolved. For the next step, you'll need a 250 centimeter cubed volumetric flask and a funnel. Pour your solution down a glass rod and through the funnel into the flask. Make sure to raise the funnel so that it drains smoothly. To make sure all of your sodium carbonate solution is transferred to the volumetric flask, you should use a wash bottle to rinse the beaker. Make sure to add this rinse to the volumetric flask each time, and do this at least 3 times. Take care as well to only use a small amount of water so as to not go higher than the 250 centimeter cube mark on the volumetric flask. The same should also be done with the funnel. Add distilled water to the 250 centimeter cube mark. Take care to observe the meniscus at eye level rather than from above or below. To make sure the concentration of anhydrous sodium carbonate is the same throughout your solution, stop at the flask and gently invert it several times. Finally, you will need to label the flask clearly, including the exact concentration of your solution. Standard solution, you first have to work out the molar mass of anhydrous sodium carbonate, as shown here. To calculate the amount of substance used, you will then have to divide the mass of the anhydrous sodium carbonate used by its molar mass. As we know the volume of the solution in the volumetric flask is 250 centimeter cubed, we can calculate the concentration. Remember to divide by 1,000 to convert the units of volume from centimeter cubed into decimeter cubed. So, the known accurate concentration of your sodium carbonate solution is therefore 0.0974 moles per decimeter cubed.
Okay, so that takes us through how to produce a standard solution. There will be a number of calculations and practice for you to be able to conduct in your booklet. And that's the end of this video. I'll see you in class.